Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
We start later.
Okay, so I'd like to introduce Sebastian Michel. And where are you from?
Lausanne, Switzerland.
EPFL in Lausanne, Switzerland. And Sebastian will be talking about querying and visualizing data cube in mathematics for environmental science applications. Or?
Yeah. Thanks a lot for the introduction. Let me put this a bit more up. Okay, this is joint work with Anjul Jain. Oops. It's not optimal. Better? Okay. Okay, so this is joint work with Anjul Jain, Calabra from EPFL in Lausanne, and Jungman Tzu. He recently joined the University of Southern Denmark. And this is the outline of the talk. First, I will start explaining what we do in Switzerland, a very short introduction focusing only on the related things for this talk. I will present then the motivation, problem statement, our approach, the fundamentals, and then review briefly the existing technology that we applied to solve the problems, present our system architecture, how to use it as an example, and then present some sample plots and conclude. This is more like an application talks than a research talk, so I would really, if you're interested in using this, please contact me after the talk and we have a look. We could make it available to you. Okay, so we are working on a Swiss experiment, obviously in Switzerland, and the Swiss experiment project has its aim at providing a generic infrastructure using web-based technologies, wireless communication, and a lot of high or low-cost sensors. And the main goal is to support multiple environmental science projects and to foster collaboration between these particular projects. The data that we gather here in this infrastructure is not only meant to be data available to the project partners, but should be somehow made publicly available so that everybody can participate in this monitoring process. This is an overview about the several projects that are working together in this Swiss experiment umbrella project. This is the map of Switzerland, and you can see it's pretty dense, and we nearly captured the whole country with pretty heterogeneous projects like hydrology projects, avalanche research projects, and so on. And whenever there is an overlap in a particular project region, an environmental campaign running there, people can reuse, of course, the data other projects have gathered. This might be, in this case here, with these meteorological stations that are deployed all over Switzerland. If you're running an experiment in this region, you might want to use a temperature as a background model or as a boundary model for your more detailed, more precise model. This is an example using Microsoft SensorMap as a visualization tool. So this is the Le Genepi glacier next to, close to Martigny in Switzerland. And there are a couple of so-called sensoscope stations deployed. These are very low-cost meteorological station measuring things like surface temperature, air temperature, humidity, solar radiation, watermark, and so on. And this is exactly this kind of data we will address in this talk. Now, in this Swiss collaboration, if you consider the previous state of people running experiments, and this was already a topic of today's panel, there is a lack of communication between scientists. Even in one institute, you hardly find people that really collaborate and exchange data due to particular reasons we're not really aware of. And on the other side, in the future, in the Web 2.0 style, Science 2.0, environmental monitoring 2.0 style information infrastructure, of course you would assume that communities share the information online. In the previous state, you have randomly distributed data files. In the near future, would have a data repository with a single point of access to the homogeneous view over the data. The previous state, data loss, future no data loss, pretty simple, right? Previous state, you don't know what happened to the data, and the future is, of course, what Juliana talked about, provenance tracking and these kind of things. Previous state is waste of resources, in particular because you replicate or you don't replicate, you don't communicate with people, and in the future we have, of course, some data reuse. In the previous state, only a small user community accesses the data, and we envision open access to the data so that the public can collaborate as well. So what we are building up in Swiss Experiment is this, actually not this, but this here. This is Microsoft SensorMap showing particular deployment in the Swiss Alps and close to Davos. And you can see we have some, or they have some basic functionality here for showing simple plots. And what our part is here, we built this Web 2.0 style infrastructure based on top of the wiki, and we can track or we can record provenance, so what happened to the data. So if people are monitoring or observing the information in SensorMap here, they would be informed over things that were going on with a particular measurement. So in this case of the station here in Davos, there would be information that, hey, have a look at this wiki to see what's going on with the, or what was going on with the data. And you can see that this station was buried into 1 meter of snow. So there was no signal recorded or whatever you can see here. It's completely useless because it was not really what you wanted to measure. So here are some observations. First, we have to deal with large amounts of data. Second, we work with environmental scientists from different domains like avalanche research, hydrology, and so on. So you have to keep this in mind when providing them with tools you find appropriate, but of course they will have to use it in the end. Obviously, scientists analyze data, applying all kind of statistics, computation to learn what's going on, and then model these things, these natural phenomena, and keep working with this. One observation is that people are very restricted in learning or spending a lot of time in learning new tools, very complex tools. Because what we found is that obviously science is what matters in the end, and they don't want to spend like months of training to use a very complicated solution for this. As already mentioned today in the panel, scientists do store data in relational database systems or files, but I agree that this is only really for storing and plain querying. So there's no fancy querying going on there. So you can imagine why. This is an example of a very simple thing you want to compute. You want to compute the smoothed ambient temperature value smoothed over an hour for a particular station of one of these deployments in the Alps. This would be how a query would look like in SQL, but you can probably understand why people are not really keen on doing these simple computations in SQL. Imagine how it would be for more complex tasks. So Christmas is coming, and this was last year's Christmas when they approached us to come up with some solution to this end. This is a problem statement and the wish list. We want to visualize huge amount of data because we have plenty of stations deployed over the whole country. We want to support features which other existing tools lack, in particular these very advanced plots that they require. And we should come up with an interaction with mathematical tools like MATLAB or Mathematica because people are already used to work with these tools. Now here's our approach. You could get it from the title already. So we make use of data cubes over the environmental data. We provide a web service interface between the data cube and these mathematical tools. And in this case, we use Mathematica for this purpose. So the tool will then provide some means to query the cube and to provide already standard plots scientists requested, or scientists told us to be implemented. And this is like this linear interpolation, for instance. So data cubes are a very well-known concept of providing very fast access to different dimensions of the data. And due to pre-computation, you can really play around with the data and project it to different dimensions and to see what's going on. And in particular, you're pre-computing already several measurements like averages and so on. And typical applications are like business reporting, marketing, and data mining, and these things in general. The technologies that we used to build this up is Microsoft SQL Server 2005 and the analysis service for SQL Server. And you used Visual Studio as a development tool, and for Mathematica we used version 7. And for the web service we used Microsoft IIS. So web services are pretty old in the meantime. It's just like a layer between applications. So a server provides some web service interfaces, and clients can call these interfaces by exchanging so-called SOAP messages, which is just an XML encryption of remote procedure calls. And in addition to these SOAP messages, which are pretty ugly to read, but you don't have to really care on this, in addition to this, you have machine-readable descriptions of the operations offered by the web service, and this is stored in this web service description language, WSDL. The drawback here is that the message size increases quite a bit because of this XML representation of the message call. So the good news is that Mathematica and MATLAB already provide calling web services. So this is already very important for our approach. And about these blow-up of the message sizes, we found that this is not a big issue for the plots that we consider. Like the amount of data transferred is still pretty okay. So for like a nice plot, you have around 2 kilobytes of data, which is still fine to send between the client and the server. And of course, you can have multiple clients connecting to one server, and multiple people can use the data cube. So this is system architecture. Here you have the data cube, the ASP-based web service that we implemented, and running in a web server, exchanging the SOAP messages. And here you have the Mathematica web service interface, which already exists, connecting to the Mathematica kernel, and then this front end that will display the plots in the end. So what the scientists gave us is the following database schema. You don't have to really understand, I guess, half of this. I don't know myself. It's very cryptic table or column names that they have. But in the end, you have several nodes with latitude and longitude information where this node was installed in the deployment. You have sensor information, which sensor type was used, like temperature measurement and so on, which is a unit. And then, of course, you have the data readings in a different table. And some configuration parameters here, quality of service information here, and some particular hardware information is stored as well. But what is really important for us here is the node information and, of course, the data that is measured. Now we build up the cube over this data by building up a view over all the measurements. So you have here node ID, sensor ID, and these things. And what is very important is that you define a timeline, and this can be fitted to the need of the scientists. So what we found when talking to the scientists, that they usually require things we would not consider it as being like a very relevant timeline to compute averages over, but they have measures like year of the day, hour of the day, and these kind of things, or of day of the year for a particular year, so they can see what's going on in a larger scale. So the steps, once you build up the data cube, the steps for plotting and having a look at what's going on, it's pretty simple. You just install the web service, which is only one line of code in Mathematica. You have to import the Mathematica packages, which you do once, and this is like only a few lines of code themselves, but this doesn't really matter. You define the data source which you want to query, which elements you want to access from the cube, like the dimensions or the timelines and so on. And you define the measure you were interested in, for instance, the average, and then our framework will generate this multi-dimensional expression query. We don't have to learn a different or another query language here. And then the query is sent to the server using web service calls, and the XML answer will be passed. And then all you have to do is you just pick the plotting function you want to use, and Mathematica will provide you the plot. This is how it looks like in an example. So you're saying you want to plot sensor ID 1, which is the ambient temperature, just an encoding for this. You're interested in the average, which is just the sum of all values divided by the count, obviously. And you can specify the nodes you want to plot. So there were like around 50 stations deployed in this deployment in the ARPS. And we want to pick these three and make a plot over these. We are interested in the several hour or several timelines, which is like, this is the hour of the day for a particular day. This is an example. Data sources is some Grand deployment in the Alps. And then you just issue the query saying get query from the data source, the particular measures and the cube elements, and then Mathematica will retrieve the MDX query, and then you can issue the query, and that Mathematica plots the, or show you the plot. Now let's come to an example of our system really what it can do. These are the so-called SensorScope stations that groups from EPFL deploy in the Alps. These are pretty cheap, low-cost stations, and they usually put them in the Alps for like campaigns of a couple of weeks, like up to 50 stations. Or even on the campus at EPFL, they had a deployment with 100 stations, but usually it's around like 30, 50 stations. You can see here, I think this is for solar radiation, wind speed or wind direction. This is the box with all the hardware communication. This is a Saint Bernard dock that they put there. This doesn't have any meaning, and so on. So you can, these stations measure the following measures here, like relative humidity, soil moisture, watermark, rain meter, and so on. And you can have a couple of calculations on top. So you can have, for instance, the average wind speed, or if you want to dive a bit more into this scientists' world, you can calculate the sensible heat flux for particular parameters here. And you can have contour plots using, for instance, this inverse distance interpolation measure. Now this is an example how it will look like in the end when Mathematica returns. This is a contour plot, and you can see here these particular stations. I hope you can see, too much light. And this is for the solar radiation. And here you have the scale and the actual measurement values. So one thing that is really important for scientists is to look at these plots, to vary parameters, and to see from these visual impressions what's going on, and then to dig in deeper into investigating the different aspects of the experiment. This is a phenomenon plot. So on the x-axis you have different days, and on the y-axis you have the hour of the day, so from 0 to 24. And you can see here that around always the same hour of the day, the surface temperature rises. And this might be, of course, if the sun comes out or behind the clouds. So here probably there are some clouds here that are no clouds, and if the sun comes, it will heat up the surface, obviously. And this happens not at 8 or at 9 in the morning, but a bit later because it takes some time to heat up. Here's a very simple scatter plot. Of course, we support also this one here. This is the relative humidity over particular longitude values. This is a wind speed plot, vector plot. So the stations and the magnitude, the wind speed and the direction, which is measured. This is a sensible heat flux plot. And all these plot people or the scientists approached us and told us what they really want to have as a plot. And each plot requires like one-time effort for writing in Mathematica package. And yes, so you do it only once for each kind of plot. And we have a couple already implemented. So in conclusion, so what we did is to build a web service interface between Mathematica and the data cube. As we learned that Mathematica and MATLAB, these tools are really well accepted in the scientist communities. And data cube is ideal for really exploring and in a very fast way, learning what's going on in the data. We have already implemented, as I said, several visualization functions in our software package, which are easy to install and easy to use. You can have, while implementing these, or you've been implementing these plots yourself, you can decide if you want to perform a certain amount of computation in Mathematica, or better push it to the data cube and pre-compute it for faster query response time. So very important thing here, we want to make it as easy as possible, the usage of the tools. Very important to note, you don't have to dive into the MDX queries and so on. This is completely automatically generated, and you will not even see one unless you want. Okay, that's the end of my talk. So if this sounds to be interesting to you and you want to use it, then let us know. So at least these tools are very easy to install. I can show. Okay. Yes.
I have a question about your data sizes. You said that you were looking at a very large data set.
Yes.
And then you said about the overhead associated with packaging data up in XML and SOAP and stuff like that. You said that those overheads were very large.
No,
Are you doing the whole data set at the same time, or are you just looking at pieces of it?
no, this blow up in message size is only if you want to have a plot, right? And the plot is a very aggregated view on the data anyway. So you will if you have like a gigabyte data, you will never have a plot that requires even like 10% of the data being transferred, right?
Oh, so you're only looking at small pieces of the data?
Yeah, the plot already aggregates everything. Like for this contour plot, for instance, had like less than a K of data points to be sent to Mathematica to be plotted. So you're really like doing the processing in the cube and then sending only the information needed for the plot. And unless you have a scatter plot with 10 million points, right? But then there's nothing you can do anyway if you want to have the plot with 10 million points.
Could I ask the same question?
Yeah.
Okay. Can you show me that contour block here, please?
Which one?
The contour block. So you have your... What are those red spots on the corner? Is this where you have multiple sensors?
Well, these spots here are the sensors actually.
Right. So how many sensors are there in that picture?
Oh, I think 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, something like this.
And you're interpolating across that whole region from 7 sensors?
Yes.
Okay.
So in principle, it would probably make more sense to consider only the hull, really. But this is up to you basically how to define the region. What? More questions? Okay. Thanks a lot.